And so the interesting thing is AI has been around since the 60s. And I think that history, that context is really important to actually understand that this has been a cumulative effect, not simply a, hey, we did generative AI and it came out of nowhere.
Think of it as like 5 R&D AI labs, which kind of grew in parallel over the last half of the century. And they had different assumptions based on which they wanted to solve this AI problem on how machines can think. Symbolists treat learning like finding rules, discover crisp if then else statements to explain the data. So Bayesians were about learning everything with probability lens. And then there were the analogizers. Their worldview was that learning is like by analogy. So if you identify anything that resembles the other, then you can predict the thing that you're wanting to predict. The fourth is the evolutionaries. So they said, all our intelligence came based on evolution, right? So borrow something from Darwin, generate a lot of candidate programs, a lot of candidate hypotheses, and then crossbreed and mutate. And then the fifth were the connectionists. The current state of AI and the things that are very popular come from this approach. So the connectionists imitate the brain. What they said is, well, we know something that is intelligent, something that does intelligence, so let's try to copy it.
Add to that, there are specific use cases that are good for all of these, right? You don't need to have full service AI for every single use case. Right now, to everybody, AI looks like a hammer and everything is a nail. And we need to be a lot more discerning about where we apply AI right now. And this is the interesting thing is there are different types of AI. Depending on your use case, you could be using one or the other, or you could use a completely different automation mechanism. And it's basically doing the fit for purpose work that I think a lot of people forget about because they just want to do the coolest, latest thing.
AlphaGo's 37th move of game 2, it put the stone in a spot that no top player would ever even think of. The commentators thought it was like a blunder until the board slowly swung in AlphaGo's favor, and even the champion Lee Sedol was like, what just happened here? If it was trained only on human games by quote-unquote supervised learning, would have never found this line of play. Endlessly played in a reinforcement learning pattern with itself, and then it found this brilliant idea. And he wrote the books of the chess and Go strategy based on what computers have found. So this move 37 became like a shorthand for AI discovering tactics which go beyond human imagination. So this is the power of reinforcement learning. It may be messy and resource hungry, but as this move 37 metaphor shows us, it's precisely that wide open exploration that lets AI leap beyond the incremental progress into something truly breakthrough.
Welcome to govai.fm, your no-nonsense guide to AI in the public sector. Connect with peers and learn from real successes, failures, and lessons from the trenches.
Before going into more detailed episodes about use cases and stuff, let's first give a background about AI and make sure that we are talking the same language.
Sure. I mean, when we talk AI right now, everyone thinks it's generative AI. And so the interesting thing is AI has been around since the 60s, right? We've had different iterations of it. We have had different versions of it, but the language nut was cracked. And when the language nut was cracked, that's what allowed us to actually unlock a lot more value and potential when it comes to AI. And this is where growth is coming in. But I think it's really interesting that even when we talk about AI models or implementing AI, we've been doing it for years and years and years. And I think that history, that context is really important to actually understand that this has been a cumulative effect, not simply a, hey, we did generative AI and it came out of nowhere.
Perfect. The motivation here was I wanted to do 3 things here. One was educate, second was inspire, and third was entertain. I'm trying to come up with examples here which are hopefully entertaining for some of you here. So let me move on.
Faith in you, Girish. Okay. You're always entertaining.
Okay, so on cue for entertainment, so this was one of the popular stories in 1990s with data and analytics and BI becoming big. And the story goes that some retailer, possibly Walmart, they discovered a correlation where people like young male in America on Friday would go to a Walmart to get diapers, and then they would always get beer, right? And Friday, men, diapers, beer, right? Everybody was then, oh, if we get this data correlation and then we can place the diapers next to the beer, so one sale helps the other sale. I don't think this is a real story. This was an urban legend that came from some management consultant groups. It was very popular at that time.
But if you think about it, I mean, it's not that far of a stretch to think that young males in North America would buy beer and diapers in the same run, because that sounds about right culturally, right?
And yeah, and on Fridays. So
And
on,
on
yeah, so
Fridays.
something about that. So what at that time everybody was thinking is like, we have data because people were collecting data and wanted to do more with data. Like, what can we do with data? And that's where like a lot of data warehousing and all become very popular, right? Like in 90s, there were people talking about our data is too siloed. Only if we get all the data together. And I wanted to place this AI and generative AI in this corporate bucket of BI. Within the BI, these terms are quite standard, and many of you listeners would know about these already. You have descriptive analytics, you have diagnostic analytics, predictive analytics, prescriptive analytics. Like those are the levels of analytics, right? So initially you make your Power BI dashboards, and that's more like a descriptive analytics. So for example, in a city, how much traffic is in which area and where are there traffic gridlocks, all of that happens in a descriptive analytics case. And then if there was some gridlock in some lane somewhere, then you do a diagnostic analysis on why it happened, where it happened. You might find that there is a school that has the same timing as some nearby office area, and that's why it happened. So that's where you're using the data to do the diagnostic analysis, right? And then the fun part starts, right? Like where you used to say, okay, can I use all this data to make some predictions? Like there are some big events coming up, like FIFA, I don't know, that you want to predict, like what might happen. Now that I know these patterns in data, how can I use them to identify what might happen? Right. So that's the third rung, third level of intelligence of for business analytics. And then the fourth level is, okay, you have the predictions. Now what interventions can I take which will make it not happen if it's an event you don't want to happen, right? And AI is used in each of these, but right now a lot of AI is done in this predictive analytics. So when you think of AI, you think of predictive analytics, but it's used throughout.
So I'm going to add to that because we're actually developing our own analytical framework within our organization. And in that, we do have descriptive, diagnostic, predictive, prescriptive, but we've added cognitive because that's the fifth branch. When you go from prescriptive to cognitive, it's really understanding and engaging in a much more, for lack of a better term, human level. Like the perception of a model is much different than what you would get in prescriptive, because prescriptive takes historical data and then creates a lens of future looking based on that historical data. A cognitive model takes a lot of different inputs and creates its own pattern of recognition and delivery. And it's really understanding the difference between these analytical frameworks that helps you kind of ground yourself in what AI actually is and how it moves through various lenses that we look at business intelligence, reporting, and analytics, because it's all a build on of what the basic foundations were.
Beautiful. So that's a great motivation for using AI in public sector and starting our story of AI. So it all starts with Alan Turing, one of the legends in AI, and he had a paper which says, can machines think? Can we have machines do the same thing, basically mimicking tasks that humans do, maybe financially valuable tasks that humans do, can machines do, right? Like, so, and that's where a lot of research started in the 1950s. And what came out of it is a Turing test, and that's still used. And basically, the motivation behind this is very simple. Instead of a person, if there was a machine answering your questions, would that machine successfully fool you into thinking that it's a human, not a machine, right? Like, and that's the foundational concept of a Turing test. And what we do is we come up with different ideas on how we can make AI fool somebody into believing that they are a human. So with Turing test, the first idea was quite simple and straightforward, and the first thing that might come to your mind, okay, we have some experts. So we have doctors, for example, who are experts and they know how to identify diseases, how to take interventions, diagnose people.
Let's talk about that a little bit. When you're diagnosing people, it's a process of elimination. Just from my own history, I was an ill child. So I ended up going to the doctor and nobody actually knew what was wrong with me. And so it wasn't a question of, diagnosing me was easy. It was a process of elimination. And so even doctors, because they have a knowledge base, they go to med school, everything that they do is a process of elimination. They do tests to eliminate certain diseases. They do tests to eliminate certain deficiencies. They do all these different tests. And some of the tests that they do might have adverse effects as well. So it's really thinking
Absolutely.
through what that process of elimination looks like, because if you understand the rules associated with an engagement, you can encode them. You can make a specific algorithm around it if you actually understand the rules of how the logic supposedly runs through
Exactly.
on diagnostic diagnostics.
And the idea initially was we have very few of these expert doctors. What if we take their brain dump, all these rules, put it in a system and make a system so flexible and make this rules engine? And that's where a lot of ideas about rules engine came, right? Make this rules engine so flexible that you can add arbitrary rules on top and link those rules together. And then you have a doctor in a computer. And then you solve a lot of world problems that way. They did well, like in a very specific contained fields, they did very well in the spirit of entertainment. One of the fun models that was done was Eliza, a speaking bot. So this acted like it's your shrink based on very simple rules. It says, you say, I am feeling a bit down. And Eliza will say, why do you think you're feeling it down today? I'm not really sure. Tell me more about maybe it's weather. Tell me more about the weather. So it's just repeating what you said in creative ways where it feels like you're talking to a human, right?
So I have a question for you. Would you
Yeah.
want to talk to Eliza if you were having a bad day?
Maybe like 50-50, right? It depends on the person, the mood. But right now we are in a chat GPT generation, but there were some simple business rules based chat GPTs that were made in early days in 1966 based on just simple business rules. And for a public sector corporation, take your big rule books, right? Like bylaws or whatever, right? And what if you could just code them as business rules and those business rules start speaking, right? And that would be the solution to all your problems.
Do you think it really is the solution to all our problems, though, Girish? Like, if machines could solve all our problems, we'd be in a much different state as a society.
So let's talk about it. So in 1980s, this one was the winning route. The people who are doing the neural networks, which are popular now, Jeff Hinton and all, were very unpopular, right? Like they were like, they're doing something on the sideline, researchy stuff. This is the real deal. This is what is going to give us AI. But this started falling apart in late 80s, early 90s. And maybe your thoughts on why might it fall apart?
Because we are not binary, right? Like if you build a model that's binary, that says if this, then that, that is not how people work. We need multiple pathways and multiple ways of moving through our decisioning because depending on the context and the rules change all the time. The context changes, the environment changes. And therefore, when you build a system that's based on rules and those rules are super structured within the algorithm, it's going to break because it can't follow all the patterns.
Yeah, the rules are brittle. They keep changing all the time. There are softer rules. Like there is no yes or no. There are many times probability of this happening based on this is
and also
more.
There's so many maybes, right? Like it's like
Exactly.
maybe if this was what's happening, then we would go this way. I wonder if that makes sense. Like for
Absolutely.
me, that's how I would interpret it because human beings are complex. And if we're trying to replicate how humans think and how they engage, then this isn't going to work.
Like not to replicate a whole human being, but a human being who is an officer whose job is to answer your questions about these rule books, or whose job is to be a doctor and do your diagnosis, right? Like even if it is in that small context, it still gets brittle and it still starts breaking.
Well, here's the thing. If we didn't need reasoning with a contextual or emotional lens, with that lens of empathy or other variables around it, we wouldn't need lawyers. They wouldn't be paid as well as they are. We wouldn't need doctors. They wouldn't be paid as well as they are because their judgment is a big part of how they get to specific answers, right? And so judgment is kind of the key thing here that's kind of missing when you do a rule-based structure like this.
The judgment comes from their experience, which means data. So the next approach was, instead of doing manual knowledge, like, if then else, what if we just give machines the data and tell them like, you become an experienced doctor by just looking at a lot of cancer cases? And there were many things like spam filters, recommender systems, fraud detection systems, a lot of things that can learn from data. But when you started thinking about learning from data, one of the things is, what are you learning, right? Like, so this is a fantastic book, Thinking Fast and Slow, Daniel Kahneman. They got the Nobel Prize on how our brain works. And our brain has two distinct modes in which it reasons and thinks, right? So the system one is the one that is quick, reactive, fast. Like if I throw a ball at you, you're not going to do a physics equation to say the ball is going to come here. You just react very fast. And that's the system one thinking. And the system two thinking is if you are doing your taxes, or if I tell you what is 34 times 28, right? Like, and whatever you are doing, that's the system two type of thinking. So then what we are thinking is, when we are learning from data, are we learning the system one tasks, or should AI learn system 1 task? Should AI learn system 2 tasks? Both of them? So that was the question.
But Girish, like, it's a great book. I agree. And it did do very well. But I don't think we're that binary, right? So in a lot of cases, especially in where you apply judgment or you're making decisions in a specific environment, you emotionally make a decision before you even understand logically why you made that decision. And then you use your reasoning, your system two thinking, to logically put that decision in the category you wanted in, but you instinctively made a decision before you even got to your system two thinking, right?
Absolutely.
And
Yeah.
this happens so much in humans. And what I find really interesting about this is we've put this as kind of a structured way of thinking about it, but have we really addressed that we use our guts a lot too when we're doing
We
all
do.
of this,
Yeah,
right?
and it's an open area of research. But what this helps is that there are two faculties within our brain, one that is doing the fast thinking and one that can do the slow rational thinking. For example, if we are trying to have a spreadsheet and based on a spreadsheet, we are making a prediction answer, we are doing some sort of a system two thinking. As opposed to we are looking at an image and seeing whether this X-ray is malignant tumor or not.
So when you have system one thinking, when it's emotional and intuitive, most of our social sciences tend to go towards that thinking, feeling, or that feeling kind of
Feeling goes
place,
there.
right?
Absolutely. Yeah,
So
feeling goes there. But it's not just about feeling, like even visual, like the way we see things and we see an apple. Or if I'm teaching my daughter what is a cat, I don't describe like it has a tail and it has four legs. I just show an image of a cat and she just, it's a cat,
she gets
right?
it.
Like,
It's a cat.
yeah, it's
Yeah.
a cat. Yeah, so we'll go more into details about it. I just wanted to linger on this so it kind of solidifies later when we bring this back again. Okay, so back to the time of Alan Turing and when people were thinking of how can machines learn. So by that time, we already had statistics, right? Like R.A. Fisher had come up with p-values and RCTs, like randomized controlled trials, things that we still use. So it's not like we were at a cold start, right? Like a lot of work was done in statistics. And one of their favorite shortcuts is the p-value. If you flip a coin and it turns out to be head, and that's fine, 50-50. Flip it again, it's second time heads. Again, common, right? Like that can happen. And you flip it again, and the third time heads. Still fine, right? Like three heads can come in a row. And then you flip it again. Fourth time it comes ahead. And now you start becoming like suspicious. Like, is this coin loaded or like what is happening? But maybe not, right? Like then you flip it again and it again is heads. So if you have like six heads in a row, then we call it something like statistically significant. Like there is a 1 in 20 shot of that happening, right? So that's significant. So that is kind of a little bit of an intuition of a p-value. Like a city department, for example, in a public sector can use the same logic. Like picture a waste collection team wondering, on snow days, our pickups are missed more. Is that statistically significant or is that just a random chance, right? So we check for like 10 snow days and then we find that 9 of the 10 snow days we had a lot of missed pickups, right? And then we say, this is like the p-value is less than the cutoff of 0.05. So I think this is statistically significant. So think of that as a starting point, and then you take that and then you extrapolate it to more. So what you say is, well, a human needs to come up with a hypothesis, right? What if I want the machine to just take my spreadsheet of information? What if you could just give it to machine and then it comes up with its own hypothesis and it decides which of these variables is important in what respect, and then it comes up with a formula. Like we are looking at a bunch of government buildings, think of it like that. So on the left hand side there is a spreadsheet, a very simplified example of course, but you have square footage of the government building, the age, like older building, newer building, and then HVAC, yes or no, is there HVAC, yes or no, and then the outcome variable, that how much was the bill, like was it high or low? Let's say we pick up some threshold, right? So there are these input variables, and from that we want to know whether the electricity bill will be high or low, right? And we have algorithms, and we had algorithms even in those times, 50s and 60s, which could take this data and would come up with the equation, something at the bottom where the energy usage or whatever the bill that you'll get for electricity would be 0.6 times the first variable of size, and or plus 50 times the HVAC yes no, let's say you make it 0 1, minus 10 times age or something like that. Then let's come up with an equation which is kind of a multiple sets of hypothesis tests like we had earlier, but coming up with an end-to-end prediction. And then we can use that end-to-end prediction to then take any new building and then predict whether there will be high usage or not, right? So those kind of statistical methods already existed. So, with that background, knowing what existed at that time, let's look into a bunch of different experiments which started figuring out how to solve AI, right? And that problem is still being solved. But what happened is these, we call them five tribes historically, is inspired from the book The Master Algorithm by Pedro Domingo, where think of it as like five R&D AI labs which kind of grew in parallel over the last half of the century. And they had different assumptions based on which they wanted to solve this AI problem on how machines can think. The first one, the symbolists treat learning like finding rules, discover crisp if then else statements to explain the data. So the second one is Bayesians, who were about learning everything with probability lens. We look at all of these in details. I just wanted to quickly go over all of them. And then there were the analogizers. Their worldview was that learning is like by analogy. So if you identify anything that resembles the other, then you can predict the thing that you're wanting to predict. Like if you want to know if a person will purchase an item on Amazon or not, then you see if the person purchased some similar items. The fourth is the evolutionaries. So they said, all our intelligence came based on evolution, right? So borrow something from Darwin, generate a lot of candidate programs, a lot of candidate hypotheses, and then crossbreed and mutate. And we'll go into how that might work. And then the fifth were the connectionists. And we are kind of well versed with these now because all the deep learning and the current state of AI and the things that are very popular come from this approach. So the connectionists imitate the brain. What they said is, well, we know something that is intelligent, something that does intelligence. So let's try to copy it. We know the brain, it has some neurons. What if we make artificial neurons and have some connections, adjust the weights, try to follow what the brain does, and we'll get AI, right? So these were like very different approaches. They sometimes borrowed math from each other. A lot of those core statistical beliefs that were existing, they borrowed from each other. But other than that, their inspiration and the core beliefs were different. So the experiments led to like different solutions, different outcomes that came out of it. And we'll dive into each of the tribe and their toolbox.
Well, I would argue that they're all like actual AI
The
is a
same.
cumulative effect of all of these, right? So they're building blocks. It's like anything. To me, this is a cumulative thing. Like all of these tribes, like people get so entrenched and it's thinking about the whole, like the whole here is greater than the sum of each individual part. And I find it so funny when people get so entrenched and so stuck in their way of thinking. They're saying, no, I'm right. And it's like, well, you're all kind of right. And it just builds on it, right? When you think about it, it's driven by all of these factors, not just one or any of them.
Yeah, this comes from is a book called The Master Algorithm, and that says the same thing. So let's go into the first one, right? Like, so the first ones are the symbolists, right? Symbolists are like the most obvious heirs to the expert systems that we just talked about. In expert systems, we have if then else rules, which are like a brain dump, we said, from an expert, like a doctor. So think of it as the same thing, but except from learn the rules directly from data. Can we learn if then else rules directly from data? So let's apply this idea to like this ice cream sales log. Again, a simplistic example, right? So there is some observed data there, like there is whether is sunny or rainy, and the time of the day, noon, morning, evening, and then whether ice cream was bought or not, right? Like, so there is like an observed log of data, right? And based on that, we want to find some crisp rules, right? So what the algorithm does, so there are some tree-based algorithms, but at a high level, like, to give you an intuition what that does, think of it as like a version of smart 20 question games where it keeps choosing the yes or no query. Like, was it sunny? And then it says, yeah, on sunny days, many bought ice cream or did not buy ice cream. And then within sunny days, where they say, okay, what was the time? Morning, noon, and then bought or did not buy ice cream. And they try to find branches which give them a very specific rule. So each path down the line of these tree will become like a sentence that will say that if it is sunny and if it is a morning, then people buy ice cream, right? Like, so you're trying to learn these rules from data using algorithms. The good thing about this is like you hand this kind of a tree to any manager and they will follow the branches and see the exact logic of the prediction. So there is no black box. Symbolist approaches are by nature much more white box, right? The symbolist approaches have their strengths, right? Learn from the data directly. That was the main principle anyway. Simple and interpretable models. We said like you could see the rules and everybody knows exactly why a decision is made, which is very important, especially for public sector, right? And they do not need any prior beliefs. There is no preconceived notions that we need to feed into the algorithm. They just take a big log of ice cream sales, for example, and they can learn. right? So that was the strength. But they had some limitations too, right? And usually your strengths are your limitations, right? So they could learn wrong things, and we know that. You could like just look at a log and that might have some biased data and you can learn wrong things. That's true about all the algorithms, but definitely about these. They had limited complexity. They had simple interpretable rules, but with limited complexity comes limited power. So they could predict like ice cream sales, but could they look at a computer vision image and identify different objects? That those rules you would imagine would be like looking at pixels, taking pixels data and coming up with what that object is, you would imagine would be much more complex, right? Like, so could you write interpretable rules to come up with that? Maybe not, right? Like, so they could, what they could solve that set was kind of limited by the complexity that they can have. And they had no mechanism to put expert knowledge. So sometimes in low data scenarios, like when you had like COVID, for example, and where you had very little data and you were trying to make some decisions based on whatever information you had coming, that there was an outbreak in Superstore near this, and I saw another outbreak somewhere else, and you had very little data, but you had some prior beliefs about how the communicable diseases work. But there was no way a lot of these algorithms that were designed for these methods could take in that expert knowledge. So where no expert knowledge required is an advantage, in some low data scenarios, you can't use expert knowledge is a disadvantage. And actually that cues in for the next algorithm, which is very good at taking prior beliefs and using that seamlessly with the new data that comes in. And that comes from Bayesian approaches. And one of the most famous Bayesian is this gentleman in the picture here. His name is Judea Pearl, one of my favorite AI scientists, a very deep thinker. And this book of his, The Book of Why, is one of my favorite books. And it's very easy read. So I totally recommend this book. But coming to the second tribe of the Bayesians, Bayesians treat knowledge as a living, breathing probability that shifts with every clue that comes in. So in this example, take a flu season, right? And a public health team walks into January already thinking that flu is a little bit likelier this month than July, for example. So that's their prior belief. Now, suppose Monday morning dashboard shows that 12 confirmed flu cases in a neighborhood this week, then the Bayesian rule steps in. It mixes the prior belief that it's January with the fresh data and cranks up the outbreak probability to from 15% to 80%, for example. Suddenly the guidance changes, right? Notify all the clinics, restock all the antivirals, like launch media alerts, like things like that, right? So what's powerful here is that gray zone thing. It's like, so the tests aren't perfect, symptoms are reported with a lag, but these Bayesian networks keep a running score of how confident it is. It's not saying a yes or no. As more swabs arrive, some positive, some negative, the math nudges the dial like up or down, right? Think about some safety inspector whose job is to make sure there are no workplace accidents, for example, right? Like at any public sector organization. And on any random job, let's say the chance of some accident happening while working, let's say 1%. And that's our baseline. And a phone rings to the safety officer and it says that I'm watching a roofing crew on Maple Street and the shingles keep sliding and they're not following all the safety protocols, right? So the words like the roofing crew already nudges the odds, because past record already says that while average probability of accidents is maybe 1%, the roofing crew makes it go 5%, so, right? And now the officer layers in fresh clues. So they said, oh, it was Maple Street, so which is an old neighborhood, brittle rafters. So it doubles again. Posterior probability is increasing as more clues are coming in, right? Then they look at the roofing company and they say, oh, they had some previous citations. So they already are prone to incidents and not following rules. So again, the probability is increasing again. And now the Bayesian rule says that there's a very high probability, so go for a quick real-time inspection. So this running dial, what the Bayesian tribe is capturing was something that was missed in the symbolist rule book, right? Like symbolist, if you have a lot of data, then you don't need these Bayesians. And in fact, the other approaches, like the symbolist approaches, are even better. But there are trade-offs. So in fact, when I was doing my master's, it was like 2002 or so. And at that time, these Bayesian network, which was created by Judea Pearl, whose picture I showed earlier, that was the AI, right? Like, so I was doing the course data mining and warehousing. And at that time, the cool thing that was taught to us was the Bayesian networks.
It's the same concept of history informing future. That's kind of more what it is in terms of how this moves, right? So, like, if you think about it, you're allowing probability just to be developed from a history, whereas if you're just using plain machine learning, you're actually building out a probability based on current data set. And so that's kind of difference. Add to that, like there are specific use cases that are good for all of these, right? You don't
Absolutely.
need to have like full service AI for every single use case. Right now, to everybody, AI looks like a hammer and everything is a nail. And we need to be a lot more discerning about where we apply AI right now. And this is the interesting thing is there are different types of AI. Depending on your use case, you could be using one or the other or the other, or you could use a completely different automation mechanism. And it's basically doing the fit for purpose work that I think a lot of people forget about because they just want to do the coolest, latest thing.
Totally. And if you don't have enough of a prior belief, like you don't have those probability tables, then these kind of become brittle. And if you have a lot of data, then the previous methods were much better, much faster than these methods. The next is the Netflix challenge. So around 2007, all these different statistical methods were doing great. And we needed some sort of the beer diaper movement to prove it, right? And that came through this Netflix challenge, where Netflix said, well, we are going to give you all our data about ratings, like people watching a movie and giving ratings, and you give a recommender system. Like they had an algorithm called Cine Match. And if you can beat it or get better, then you get $1 million, right? And a lot of people used a lot of these algorithms that we talked about. Many times there was a combination, as you said, right? Like, so they took many algorithms, combined them into an ensemble, and that outperformed any individual algorithm, right? Like, so
I have been working in this space for 26 years. Some things just make sense. Let's talk about the weakness of that just quickly. Like the weakness of this is, could anyone have predicted 2025? Could anybody have predicted what's happening in the world right now? Right? And
yeah.
maybe, yeah, to some degree. I mean, okay, I'm going to say it. I'm going to be political for a second. The US going full fascist was on nobody's Uno card at this point. So there is that, right? Like thinking about past predicting history, we could arguably say that the 30s Germany is very, very a compelling argument that the past does represent the future. However, nobody predicted that it would be the US who falls back into this pattern, right? So there's a lot of things in there that are a bit of a weakness in this model.
And that's a weakness in all of AI. And there is another book, which I have at the end, which talks about this in a lot of detail. So next, let's meet the analogizers tribe. Their instinct is instead of writing if then else rules or juggling probabilities like the previous ones have done, their instinct is to review past examples, find the closest match, and copy whatever, solve the problem. In this case, for example, picture a city permit officer here, and a homeowner submits a plan for a small 10 by 12 backyard shed, right? The analogizer algorithm turns that input into a mathematical vector, like all the details about that case, like size, zoning code, setbacks, material, all of that. It creates a vector out of it, and then it scans through thousands and thousands of permits that it has done before. And then let's say it quickly finds a dozen of nearly identical sheds, and it sees that they were all tracked through the same approval process. Now, because this new request is same as all those 12 twins, the system instantly labels it with the same category, right? Let's say if it finds out of those 12 matches, like 3 went one way, 4 went another way, and then the remaining went a third way, right? Then it says that I'm not confident about the answer. So that's like the intuition of the analogy-based algorithms. So the advantage here you can think of is it's much more explainable, right? Like if you can say why did a case go this way versus that? Well, because of these other examples from history that it learned from. Remember, we are still talking about machines learning from data, right? So in that context. So it has an advantage there, right? But as the problem gets complex, right now we just had like 3, 4, 5 input variables. If the problem is very complex, then this finding quote unquote similarity becomes hard. It's in practical sense, there's a lot of problems there. Also, if you have some new cases which are not really similar to many of the cases or which are similar to very few cases, something like that, then again, we have a problem. So it has like a cold start kind of a problem in those cases. But we still see this kind of intuition in real world scenarios, right? Like a doctor consulting past patient cases to decide what kind of treatment to take. So it's kind of the same intuition. So this is another way to look at it, right? So one of the common examples of where analogy-based algorithms work is recommender systems. So in this case, for example, you're trying to have a recommendation for this on the left-hand side. You can see the user in the blue. We want to recommend something to read. And what you do is you take that user and you find other users who are very similar to that user in whichever vector, like however vector you define the user. If you like, age, gender, whatever genres they have clicked, they are interested in, things like that, right? And then you say, okay, all users who are similar to this user also read this, and that's why would be interesting. So that is a classic example of analogy based thinking and reasoning, right? On the right hand side, you will get the same thing, but from a different perspective. Where earlier we were trying to find a person who is similar to another person, you can solve the same problem by finding an article that is similar to other articles. So we can say that this user for whom we are giving a recommendation, they have read these articles, and I have many other articles which are very similar to this article, for example. So the article similarity, you again identify mathematical vectors for these articles and identify some similarity, and that will solve this problem. So that's kind of the intuition of the analogy based cases. So far, we have been focused on supervised learning. So feeding in examples to the model which have some inputs and then what is the correct label output. And then we are telling the model to learn some rules out of it, right? And this is called supervised because the model is being supervised by the data to form the rules to map from input to output. But what if no label data exists? And this is a different kind of a problem formulation. So picture a city's 311 inbox overflowing with a bunch of free-form text complaints, right? And let's say we have no buckets. We simply want the algorithm to bucket similar messages together without even telling it what the buckets are or what departments are or anything. So this is called unsupervised learning. So the model is digesting a lot of raw data and self-organizes into its own clusters. And you would have seen this before. In your phone, when you see photos are automatically grouped by people's faces. And we are not putting a tag on which person has which face and all. It just automatically clusters, bunches things together. So this is unsupervised learning. The same similarity-based logic, like for unsupervised learning, can be used for spotting anomalies in transactions for fraud detection, for example. So there are other use cases that will have this problem formulation of unsupervised, where I just have raw data and just identify anomalies for me, right? Something like that. One of the algorithms in this tribe, the analogy tribe that we're talking about, is called K nearest neighbors. It's a popular algorithm where for a given case, we find K, which is like a number, right? Like 10 nearest neighbors. Find the 10 nearest neighbors as in 10 nearest cases to it, or 10 nearest articles that are the nearest to this article, like something like that, right? So it's called K nearest neighbors. And this algorithm is quite natural to solve the unsupervised learning, although it can be used in other settings too. It's very natural for this unsupervised learning. So yeah, that was the intuition of the third tribe, the analogizers. Now, while the analogizers solve things by asking, have I seen this before? What are the things that I've seen before, the nearest neighbors? The next tribe dumps the similar example and asks the question, what if I just try a bunch of crazy ideas and see which one sticks? So that's the evolutionaries. So more than 160 years ago, Charles Darwin noticed something amazing in nature, right? If creatures keep having slight different babies and only the ones that are fit survive long enough to pass their traits, the new better designs slowly appear for all of them. No engineering is required, right? Like, so that's our evolution. So 1960s, a group of computer scientists wondered, like, could we get computers to solve the problem the same way by unleashing a bunch of random guess algorithms, random guess solutions, and letting the best ones, like relatively the best ones, survive and reproduce. By reproduce, you would like change a little bit in them and then again have a next generation, next round, right? They built algorithms that copied the basic rule of survival of the fittest and improved the solution generations over generations by just sheer trial and error, right? But and this is the intuition behind the evolutionary approaches, and these are not very common. Like a lot of ML AI right now, like we don't use a lot of it, but there are still spots and pockets within it where it is used. One of the reasons it's not very common is because these algorithms stumble forward through thousands of random mutations. They can be very slow. Like you don't know, like at what mutation, like how many years, like evolution, how long did it take for them to reach to our stage, right? So they're very slow, very messy, completely unpredictable. You never know whether the next generation will finally crack the problem you're trying to crack, or will it just keep wandering in genetic wilderness, right? If you will. But this approach did pay off in some cases. So for example, this weird looking thing here is like something that came out of the genetic algorithm for NASA. So NASA asked one of these evolutionary based programs to shape a spacecraft antenna. Okay. The result looked like a twisted, weird thing, right? That a human designer would never sketch. Yet in test, it outperformed the neat textbook antennas that we have been creating. And actually, it flew on a satellite. That's pretty cool, right? Like, so they were looking for this best radiation pattern, and they didn't tell the algorithms that what is a radiation pattern, how to go about designing an antenna. It's just like just mutate and just keep mutating and find some pattern. And it found this pattern, and it seemed to be better than anything else, right? So these algorithms can be tricky, and often they need like a lot of computing power because they keep going for a long time, right? Even how to tune them and all, there is no clear way. Like, is there a way to tune evolution so that we can start with amoeba and reach humans or whichever, the next stage faster? Like, we don't know all the knobs that are still there, right? So still they remain valuable tools for some specific things. So for example, even in deep learning, we haven't reached connectionist and the deep learning yet, but in machine learning, deep learning, there are a lot of knobs and settings like learning rates and layers and all, which we'll look into later. And to find the best fit for them, it's a very hard and messy problem. And that is one of the places where some of these algorithms are used, and discovering like robots and optimizing complex engineering layouts, some places where ordinary math just gets stuck, like these algorithms work very well. This is something similar. So picture an orange stick figure like this wobbling down a hallway, right? Nobody hard-coded a perfect walking routine for this, right? Like we haven't coded or planned it like that. The computer simply just nudges it and says, try to move and see if you fall. And every step that it keeps upright, it earns a thumbs up, let's say, right? And whenever it falls down, then it gets a thumbs down, like some sort of an algorithm that just keeps giving thumbs up and thumbs down. And it's not saying like, take your leg up in the right angle and this and that. It's not telling it anything, just giving thumbs up and thumbs down. Then after thousands and thousands of stumbles, the little guy figure starts having a smooth walk. And this is a new formulation, like this is a new problem formulation. So this is called reinforcement learning. So while again, we are looking at supervised learning where we take labeled data and then algorithms find the rules out of that data. And then we looked at earlier unsupervised learning where we take just raw data and you just identify different buckets where that raw data is going. This is a third formulation. This is like choosing a chess move, like the next move in chess, right? Like we haven't seen all the moves, and like in this kind of a board situation, the next move is this. Like we don't know, right? Like you're just giving it a thumbs up if you played those moves and eventually you reach a better position, or steering a robot through like traffic, like like auto driving cars. So there is no right answer key, right? Like the agent has to just poke through the world, notice what works, and tweak things on the fly. Now, AlphaZero in chess did exactly this. It played games with itself like millions of times, right? And it remembered all the games in which it succeeded. It got a thumbs up. On the games it was like really bad, it just gave itself thumbs down. But this simple learning, like you train your pet this way, right? Like you give a punishment or you give a reward, right? Just that simple concept, if you turn it into an algorithm, then that's exactly what beat the human world champion in chess, right? Like the grandmaster in chess, and that was AlphaZero. Again, this method is very like messy, trial and error, a lot of compute, but it still shines in things like robotics, video games, AI, and even like final polishing of the LLMs, right? Like large language models, the way they are trained, they're broadly trained in two steps. So first is like the chatbot is just reading a bunch of text and everything on the internet, right? Like that's step one, the huge training step. But in the second step, it's called alignment. And all these labs like OpenAI, they do it. So this is where you're kind of teaching LLM manners almost, right? Like, so you're telling the LLM that now you have a bunch of text, but when you chat back and forth, one, you have to listen to the user, but don't listen if it is harmful or biased or like whatever you want to define as your manners. There is a word alignment. We use it like the second step in LLM training is alignment. And for that alignment step, this reinforcement learning problem formulation is used and it works really well. This is a good metaphor. Like chess, there is another game Go, and it's even more complicated than chess, right? And AlphaGo was a program that learned to play Go, and it was playing the world champions at that time, right? So in 2016, the match was with the world champion Lee Sedol, who is thought to be like a super genius in this game. So AlphaGo's 37th move of game 2 it put the stone in a spot that no top player would ever even think of putting that stone in that place, right? So the commentators thought it was like a blunder until the board slowly swung in AlphaGo's favor. And even the champion Lee Sedol was like, what just happened here? And AlphaGo won, right? If it was trained only on human games by quote unquote supervised learning, would have never found this line of play. The only reason it found this particular completely different line of play is because it endlessly played in a reinforcement learning pattern with itself. And then it found this brilliant idea. And that's how now, you rewrote the books of the chess and go strategy based on what computers have found. So this move 37 became like a shorthand for AI discovering tactics which go beyond human imagination. So, this is the power of reinforcement learning. It may be messy and resource hungry, but as this Move 37 metaphor shows us, it's precisely that wide open exploration that lets AI leap beyond the incremental progress into like something truly breakthrough. Now, I wanted to clarify something. When we are talking here, we are talking about two different dimensions. We talked about the tribes and we went over the symbolists, the Bayesians, we did the analogy based tribes, and then the evolutionary based tribes. And right now we are talking about the evolutionary based tribes. Very soon we are going to come to the connectionists, the neural networks based tribes. But those are the tribes, those are the solution patterns, right? And while describing those, I was also talking about some problem formulations. So I said there is supervised learning, so on the right hand side, which is like giving the model inputs and outputs and having the model imitate based on the inputs and outputs, like chest X-ray, and this turned out to be a malignant tumor, and you give hundreds of examples of inputs of an X-ray and an output of what kind of output you want. So that's the supervised learning. And in the unsupervised learning, we said raw data and just bucket those raw set of complaints. And then we looked at reinforcement learning, where you're just identifying what is the best next step, right? So sometimes there is a temptation to have an association between the tribes, which are more like solutions, to the problem formulations. Like symbolists, traditionally supervised, and analogizers, we were talking about unsupervised k-means, clustering kind of based. And then we talked about evolutionaries, and that time we said there is like some philosophical similarity with the reinforcement learning. But these are just loose connections. There is no direct association. You can solve any problem using any solution, right? So instead of thinking in like that kind of silos, the better way to see it is the problem formulation on the right. It's defining the goal of what we want to solve. And the tribe and the solutions that the tribes are bringing and the intuitions that the tribes are bringing, think of them as your strategy to solve that problem.
All of this connects. Like, I don't know if you know this, my sister has a PhD in neurology and she taught brain and behavior. She did a lot of work with machine learning as well. So she's got a computer science concentration with her PhD in neurology. And so we talk about a lot of this stuff kind of offline to talk about behavioral design, essentially. The thing is something as simple as a concussion can change someone's personality so much that their past behavior is not a prediction of what their future behavior is going to be like. So the variables are so unstable, right? They're so unstable that
too many combinations.
There's way too many combinations, and humans are at the best unpredictable. And we hope we follow a simple pattern, but we also sometimes don't, because art comes from that difference that we have, that lens that we have. So part of this is just making sure that we don't denigrate those differences that actually create the beauty in the human experience as well, while still going towards machine learning and various types of AI. The other part is we have capacity for beauty and interpretation and perception that's very, very different. But what machine learning has, what algorithms have, is the ability to exponentially push a specific concept so far and train and do trial and error continuously in an ongoing manner that they don't get exhausted. Our brain craps out at certain points. We're bored. We don't want to do this anymore. It's too annoying. And then we're like, okay, this is enough. Like, enough's enough. I tried as many different things as I wanted to. Now I'm good. I'm gonna accept failure. I'm gonna move on. Machines don't get exhausted. They don't just be like, I'm bored. I'm gonna move on. They'll just keep going. And that's the thing.
And that's why evolution is so slow and messy and takes a long time, right?
Yep. Because we get bored. We're like, I don't want to do this anymore.
Yeah, and just the nature of trial and error is you need to explore too many options here.
Yep.
So what that brings us to is there was a group, the fifth tribe, that was working in the background slowly, starting with 1950s. And then there were people like Jeff Hinton who were trying to say that maybe we'll just mimic the human brain. We can talk about the neural nets and some of the things that they made happen, and we can continue our story from there.
I think it's important. Like, we need to set the foundations because people are so confused about what AI is. And I'm hoping it resonates, but if it didn't, like, we'd love to get questions.
Perfect. So for continuing this journey, if you are either of educated, inspired, or entertained, then look out for our next episode.
Looking forward to it. Thanks,
Cool.
Girish.
This was govai.fm. Connect with us on LinkedIn, suggest a guest, and stay tuned for real stories from AI in action.